20.
Oh.
We need them to start, yeah, I know. We should just start with
Just a little intro.
Supposed to read us.
A little intro later on the presentation.
Is there a story?
It's like in every presentation I do.
Yeah, you can always introduce yourself. Hi, my name is Eric Yanni, and today I'm going to talk about whatever.
Nice. You can just put the abstract in this one. So Eric, if you want to start researching the abstracts, I'm just kidding. You don't have to, it's okay. Wait, oh, Kristen, sorry. So we started notes. Yay.
Hi, Kristen.
And we figured out that sines and cosines, when you put together all the different pieces from the unit circle, and the angles, guys, wait, which axis is the angle again? Yeah, the x-axis, right? Aren't those where my pi's are? The x-axis are my angles. That's my x, but we're going to call it theta because that's where my angles are. And then what does the y-axis stand for? 1/2, that's here, right? Root 2 over 2, that's here. Root 3 over 2, that's here. What are these? 0, 1. Yeah, what they equal, right? We could say it's their trig ratios, their trigonometric ratios. Okay. So we figured out that sine and cosine. Now, hold on. Can you get your calculator to look like this? You can graph stuff in your calculator. Go ahead and open up your y equals. I want you to throw in sine of theta and throw in cosine of theta. Not literally throwing it in. Don't throw your calculator.
It's cosine of x.
Yeah, you can't use theta in your calculator, so you can use x. Oh, it's on the x-axis anyway. Cosine of x and sine of x. You're going to use x because we can't use theta. Luca just has a straight line. Does anybody have a nice little curve?
Yeah.
What's the difference? Someone that has a nice curvy thing, go to your mode. Are you in radians or degrees?
Degrees.
Wait, which one?
Radian.
The wavy ones are in radians. The straight lines, what are you in?
Degree.
Ooh, why? Why would that make
We got to
sense?
keep changing them.
Because the graph is
Why is the graph in radians? Hold on, how big is radians?
Oh, because it's in
Pi is 3.141526. 2 pi is 6.28. Well, hold on. Will Zoom standard, oh, it's frozen. Like, what on earth? Will Zoom standard let me see 2 pi in radians? We just talked about what radians are, right? 3.141526, 6.28, etc., for 2 pi. Would Zoom standard be a good window for radians? If it's like by 3 and 6, etc., for sine and cosine. You guys are so helpful. Hold on, let me come. When you graph, this is Zoom standard. -10 this way, 10 this way, right? My question is, does -10 to 10 show you a lot in degrees or a lot in radians?
It looks pretty sick.
Oh, wait.
How-
Hold on. I know. Shh. Okay, shh. Come back. In your window. I'm trying to explain to you why you got straight lines. Your window. 10 tick marks, right?
Yeah.
How many tick marks would it take for me to see a lot in degrees?
Ooh. 101.
Oh.
Like
360.
360, 180. I need a lot of tick marks, right? Radians, though, 2 pi is only 6.28. So I don't need a lot of tick marks. Now, how would I make it look good if I am, which I am, in degrees? What do I have to do in my window?
You have to stretch it.
Ooh, really stretch it, right?
You have to stretch
Can I just go, we'll just do this, right? We can do more, but we'll just do -360. That's negative, that's not going to work, right? Calculator's going to get mad. Let's see if this is a better picture.
oh, hey, it worked. Yeah, but it's just not.
It's just
You
not,
see,
it's not.
go attention.
Doesn't that take too much work? So, we could do degrees, and even though we like degrees, maybe we'll do radians as much as possible. Let me do radians first, and then do Zoom standard. Okay. Still kind of small though, right? Is there a Zoom that maybe you haven't used very much?
No. Tell me
Oh, this is so much
What?
better.
Show me this.
Oh, look at this one.
Hold the phone.
Now wait a minute, why is this cool?
That's hard.
It zooms in a little bit, but guys, hold on. Can we see if Zoom Trig understands the differences between radians and degrees?
Why not? Let's see.
Let's hit Zoom Trig again once we put it in degrees. Wow. It does it for you, but wait, look at your window. What did it change? Oh. It's going now. It probably should have gone a little bit more, but for some reason they made the preset to be negative 6.15 instead of negative 6.28. Either way. But aren't they using? Wait, am I in? Am I not in? I'm not in. That's annoying. Hold on. What happened? Enter. 3. It did work in Zoom Trig, right? Hold on.
It worked.
Wait again. But it's not a line. It's a nice, pretty. Oh my goodness. Okay, look at that window. Does it make it more degree-ish? Do you see it?
Yeah.
It makes it more degree-ish, right? Why is it going by 90s?
Because we're in 360, 360.
Angles.
Right? Isn't that kind of what I went by over here?
Yeah.
Pi over 2, pi 3, pi over 2, and 2 pi. Okay, so anyway, if your graph ever looks funky, and if you have anything with trig, maybe you should try that Zoom Triggy thing, yeah?
Yep.
So let's go back to radians, because as you guys noticed, that's easy. Zoom standard doesn't get confusing. I'm going to do Zoom Triggy again to make it look nice. And there we go. All right. My ones who are skipping ahead, yes, you can graph tangent, or 1 over cosine, or 1 over secant, or 1 over tangent. You can have some fun with that. For instance, if you were to go ahead and graph, hold on. Who's 1 over sine? 1 over sine is cosecant, so I can do 1 divided by sine of x. I wonder what cosecant looks like, and if it has anything to do with sine. It bounces.
Yeah, but that's also when you do 1 over cosine. When you do 1 over cosine, then you have
Or is so.
Okay, hold on. Too much fun. Let's talk about the graph some more. Too much fun.
That's what I'm gonna do for the rest of the class. Just kidding.
Wait, why is there a page on key points and we have to sketch these.
Love this.
We have to sketch these. Yeah, sketch these wavy things. Now, if I just said, okay, no big deal, just start sketching. Do you really want to go through the entire unit circle for all these different trig and have to sketch them? No. So instead of making you graph these point by point by point, and there are tons of points. Instead of making you graph them point by point, just like we did with transform functions before, I'm going to point out the key characteristics of the graph. And if we can get the key characteristics of the graph, you can be able to graph them like that. As long as you learn the key characteristics. But you won't have to go all the way through a unit circle and trying to find all these different points. That would just be tedious and annoying and kind of long. So, what are key points? Intercepts, maximums, and minimums. Key points, key numbers, yeah. Kind of similar. Just think key is important. So, okay, important points for the wavy things. For the sinusoidal. So fun. Sinusoidal. Not even accent, even though you don't. Oh gosh, it's sinusoidal. These are the important parts. Now, I've shown you one cycle of sine and one cycle of cosine. From beginning to end. A normal parent function cycle. Ooh, parent function. Parent function. We talked about parent functions when we were getting ready to transform stuff, right? And parent function specifically, this would be happening, cosine would be happening for being at the top or hitting the top on the y-axis as the parent function. Sine, when it goes through the y-axis, it's actually in the middle. It's at 0. Cosine's at the top. Sine's in the middle. Their waves end up looking alike, except they're in different places. They're shifted. They're transiting. what else do you know about sine and cosine? We know how high and how low they go, right? But before we go into all that craziness, I just want you to look at this example, okay? I've written down the key stuff. There are 5 important points per cycle, however you cut it. Sine has middle, top, middle, bottom, middle. Cosine has top, middle, bottom, middle, top. Basically, sine starts in the middle and then cycles. Cosine starts at the top and then cycles. That's how we know. They're found every 4th period because to put 5 points, we're going to cut the section or the graph into fourths. Do you guys see it? There's 1/4, 1/4, 1/4, 1/4. These 5 points section it off into 1, 2, 3, 4 pieces. 1, 2, 3, 4 pieces. But can you just tell me, what transformations happen to sine? What transformation is happening? Good. Vertical stretch by a factor of vertical dilation, but it is going to be a stretch. It's by 2. A vertical stretch by a factor of 2. Okay, question, what's going to happen to all your y values? Big rubber band, right? The y values is going to stretch. Now, I want you to look at the graph you just graphed a second ago. Question, how high did we go on that one? 1. So instead of going to 1, where are we going to go? To 2. And instead of going to -1, where are we going to go? To -2. Now, how will we get that graph in there? Well, hold on. Who is this? Sine or cosine? Does it start in the middle or start at the top? It's sine, right? 2 times sine. So it's the one, you can look up above. It's the one that starts in the middle. So question, if I stretch it, does the 0, 0 point go anywhere? No, it stays the same. Okay, well, what was another important point? What was this point? What angle was this point at in the parent function? Pi over 2. So we're going to go over to pi over 2. Oh, hey, you know what? Let's just do 2 pi. Let's cut it in half. That's not half. Hold on. Why am I doing 2 pi? Do you guys remember that cosine and sine cycle every 2 pi? Yeah. Do you see me showing all my quadrants? 0, 90, 180, 270, 360. I'm just showing my quadrants. Now, hold on. Pi over 2 in the original one went up to what? What's sine of pi over 2? 1. But it just got doubled. So sine of pi over 2 is now going to be, I should say 2 times sine of pi over 2 is going to be now 2. It's going to be higher. At pi, where was the original function at? You see it? Look at your graph. At pi, sine is at 0. That's going to stay the same. At 3 pi over 2, where was the graph? Yeah, do you see it? Didn't it go up and then middle and then down? Look at your graph. You're like, what graph? Right here. See? 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 3 pi over 2. Where is sine? -1. But where is it going to get stretched to be? -2, right? So it's going to be down here. And then it's going to be back to 0. Now, do you see how I was able to use just these 5 points to go ahead and get my sine curve? And can't I keep going approximately with what it's going to look like? That makes sense. I only needed 5 points. Now I could have gone to all the different pi over 6 and pi over 4, pi over 3, and had to get decimals and approximate, but I really just needed, what points did I choose? What are these points? The intercepts. The zeros of sine. And what are these points? The maximums and minimums. So when I say key points up above, I'm saying you really only need 5 points of a transform function. Then you can connect and say, hey, there he is. Let's just keep on cycling and waving, right? And then we have our graph. However, do you think that's the hardest that the transformations are going to get? So I'm going to try and simplify this process and not just say, okay, just memorize those 5 points and do all the transformations. We could do that. But there are some tricks as to how to break this down into different pieces. Here's a formula. And all I'm doing, guys, is showing, let me bring it down. All I'm doing is showing all the different transformations that can occur, okay? I'm showing all the different transformations that can occur. Do you guys see addition on the outside? Okay, you too. or subtraction on the inside. Multiplication on the outside, multiplication on the inside. Those are all of my possible shifts. All of my possible shifts. And dilations or stretching compressors. Stretchings, compressings, how do you say that? That's awkward. All the different possible dilations and translations. There you go. All the different possible dilations and translations. Now, the one that you see in the big old yellow, whatever that is, the one's being highlighted is what you will be given in a problem. The one that's highlighted is what you will be given in a problem, typically. But this is what you want. So hence why I wrote both. You'll be given usually the top one. Sometimes we'll give you what you want. But you'll be given the top one, and you want the bottom one. Why? I'll show you in a second. Let me just go ahead and label stuff, okay? Addition on the outside is technically, like old school days, we would call that, oh hey, you have some sort of vertical shift. The little a is being multiplied on the outside. Ooh, you have some sort of vertical. I'm going to say dilation because it could be a stretch or it could be a compression. The little b, it's being multiplied on the inside, even though it's the outside of the inside, still on the inside of sign. That's going to be a horizontal dilation. And then c over b, that's going to be a horizontal shift. But if I just left it like that, I'm not really shortcutting anything. If I just left it like that, I pretty much just told you what you already kind of know, and you're like, great, but science waves are ugly, so this is going to be hard. Let me give them different names. Just one second. Let me give them different names. G is going to be the placement of our sinusoidal axis. A is going to be the amplitude of the wave. How high, how low? We're going to amp it up. B is going to be, well, B is a little tricky. But B is going to be used for, he's not exactly anything, he's used for the period. There's a formula that will go along with it. He's used for the period, how long it takes for a wave to complete. And then C over B is going to be what I call the phase shift. But the phase shift we could call the initial point. The phase shift or the initial point. Giving them different names because they're going to kind of have different applications whenever we're talking about a wave. The one that probably makes the most sense right now is amplitude, like amp. Amp it up. Big sound waves get taller, as they get stronger, right? Do you guys ever watch the, I don't know, like the sound mixers and stuff you can actually see? So if we're thinking waves, wait, sound travels in sinusoids, like in sines and cosines? There's a lot of stuff that moves in waves. Anyway, amplitude, how high, how low. That one probably makes the most sense. But let's go ahead and keep looking, though, to see if we can kind of work out what on earth is going on with these different terms. We're not going to get all the way through. Obviously, we're just starting this section. Real quick, as you guys are starting, we're just going to start working out what these different things are. Some of the terms I introduced might be new. They might not, if they're not new, they're at least somewhat unfamiliar. They're not second nature to you. But as you guys are writing, okay. Chapter 3 test. I was like zooming through it. I'm like, oh, it's going to be easy. I can finish it quick this morning. And then the back page. We didn't like that back page. However, I will definitely have them done. I have a free period and 2 periods. And I will have them done by the end of the day. Why am I telling you that? Some of you really want to know what you got. Some of you really don't. Okay, you can have a better weekend by not knowing. Just kidding. Some of you might have done well. But if you really want it, you can come in, look at it, A, just to see what you got right after school real quick. You can come get it and pick up a correction paper and use a little bit of extra time to be working on test correction so that you don't have to stress about it next week with everything else we're doing with Thanksgiving coming. Anyway, just some ideas if you're gonna have time this weekend to work on math besides just catching up if you are behind. So my advice would be to come in and grab your test, but I'm allowing the possibility for some of you that are like, I'd rather just wait to do that as well. Sound good? I didn't finish everybody, but there were quite a few that did not like that back page, and so I'm trying to go through and give partial credit for what you did get, but it's really wrong. Give it a word problems, but interesting one and a couple equations and advertising. Anyway, that's what I'm about. Kiddos, we have some work to do. We do. But I'm going to go ahead and, give me 1 second. I'm going to go ahead on Monday and get to this cool little summary page that says, hey, take any sine or cosine in this weird form. And we're going to make little handwriting lines and figure out where to put special points, and then we're just going to make waves. Does that sound good? But not in a bad way, in a good way. All right, cool kids, have a great weekend. If I were you, I would not start this homework. If I were you, either come and get your test and work on corrections or catch up in something else this weekend, okay? Okay. Bye, guys.
Practice after school.